Hello, everyone. In this talk, we're going to discuss how to estimate the pros and cons of using software dependencies. And I will present the novel metric, technical leverage, that is simple to compute and yet very powerful. Technical leverage helps us measure the security risk of a software project being affected by vulnerabilities introduced by its software dependencies. This work was done in collaboration between the Cybersecurity Research Lab of the University of Trento, Italy, and the Foundational Security Research Group of the Vrije Universiteit Amsterdam, the Netherlands. The research was partially funded by the Horizon 2020 Assurance project. Let me start with a brief discussion of the changed nature of software development. We used to think that software is a monolith, single block, completely controlled by its developers. That the software project is mostly homegrown, and it is developed by a group of developers who are in full control of their code. So, in case a security vulnerability is discovered, developers can access the vulnerable place and fix it. However, it's not exactly the case. Nowadays, software developers use free open source software libraries as building blocks of their software. In particular, open source software libraries developers reuse the already existing functionality from FOSS libraries by including them into their projects as software dependencies. In this way, developers can focus on the functionality that distinguish their project and rely on third-party libraries for everything else. Such practice has led to dramatic changes. For example, for proprietary software, the fraction of homegrown code is only 5%. And dependency code is 4 times bigger than own code as industry average. Impressive, isn't it? 95% of a project code is not written by its developers. Moreover, very often, developers even do not have any idea about what happens with this borrowed code. They sometimes even do not know about its presence in their software. But the code coming from dependencies is still code. It still can have bugs and security vulnerabilities. These vulnerabilities are fixed by developers of these upstream projects. So you see now that developers are not actually riding on a big, stable, and controlled rabbit. Instead, they're trying to balance on a pyramid of many quickly moving rabbits, software libraries. In case of a vulnerability in such a block, this vulnerability affects the dependent project as well. Often it cannot be directly fixed by developers. They have to wait for a fix coming from the developers of this particular dependency, and only then adopt the fixed version. In case there are serious vulnerabilities introduced by dependencies, and these vulnerabilities are not fixed fast, they might actually crash the dependent project. So we need to have an indicator that helps us understand when such crash may happen. For this, we refer to the concepts used in finance. In the past, finance concepts have already been applied to software, in particular, the concept of financial debt. In finance, people borrowing money, while in software, people borrow code. They already developed functionality. For this, there was a term, technical debt. Technical debt refers to the short-term developers in action that may lead to a later cost of maintenance. So, for example, the concept of technical debt can be applied when developers are checking Stack Overflow and reuse some fragments of code from the suggested answers in their software projects. However, the DAX2 seminar 1662 stated that technical debt is attributed only to internal system qualities of software project. And therefore, the concept of technical debt does not apply to usage of software dependencies. However, the depth of dependency code needs to be considered. For this, we introduce the notion of technical leverage. Again, own code is the part developed by software developers for their project, while dependencies, both direct and transitive, are the others code that developers leverage on to reuse the already existing functionality and develop their projects faster. In finance, people leverage money to multiply their income. and the leverage is computed as the fraction of debt and equity, or others' money to your own money. We borrow these concepts and apply it to software. Technical leverage is the fraction of others' code and own code, or all the code of software dependencies and the own code of software project. Notice that in finance, leverage multiplies incomes, but it multiplies losses as well. And therefore, high leverage can lead to a crisis. Similar situation may happen in software. Leverage allows developers to develop their projects faster and focus only on the distinguishing functionality. However, it increases the size of the uncontrolled software code used by the project, and therefore it increases the risk of having a security vulnerability. Additionally, we introduced the change distance and change direction metrics to measure the qualitative changes of a library between two consecutive versions. These metrics capture the polar coordinates of the changes in the plane described by the sizes of own code and third-party code. Change distance characterizes the amount of change in code size between two consecutive library versions. The bigger the change distance, the bigger was the change between two consecutive library versions. Change direction characterizes the type of evolution of a library between two consecutive versions. And for example, an angle of 0 degrees means that developers purely adopt new dependencies while they did not touch their own code. An angle of 90 degrees instead means that in the new version, the developers is improving its own capital code while keeping the same third-party code on which is old version is leveraged. Various values of the change direction metric might qualitatively describe developers' actions. For example, if theta is around 90 degrees or around 270 degrees, then developers are mostly working with own code of their project. By around, I mean plus minus 45 degrees. If the value of theta is around 90 degrees, then the developers increase their own code. While the theta values around 270 degrees reveal that developers mostly reduce their own code. Similarly, if theta is around 0 degrees or around 180 degrees, then developers are mostly working with project dependencies. If the value of theta is between minus 45 and plus 45, then developers mostly adopt new dependencies. While the theta values around 180 degrees reveal that developers mostly remove dependencies of their projects. Considering these changes, we observe that theta values in the range between minus 45 degrees and plus 135 degrees correspond to the situation when developers mostly increase total code base of their project. Most likely, in this case, developers are adding new functionality to their projects. Hence, they either increase own codes of the project or increase the size of project dependencies. On the other hand, the values of theta between 135 and 315 degrees correspond to the situation when developers mostly decrease total code base of their project. Most likely, in this case, developers are optimizing their own code or the dependencies they're using. For example, they can remove some dependencies that they do not really need for their projects. Now let's observe how the proposed metrics, technical leverage, change distance, and change direction apply to the real-world software projects. For this, we selected the 200 most popular forced Java libraries used by multinational software development company. They used it in its customers or internal production level software. This resulted in more than 8,000 distinct library versions or GAVs in Maven terminology. For simplicity, in this presentation, we focus only on leverage on direct dependencies. The first analysis. So first, let's analyze how leverage helps measuring security risk of a library. To plot the graph for this analysis, we identify the maximum technical leverage and the number of vulnerabilities affecting each library in our sample. For example, we look We took all the instances of library AD and identified the version with maximum leverage. Then we computed the number of vulnerabilities affecting this version. We repeated this for all libraries in our sample. Then we grouped the leverage by the number of vulnerabilities and plotted leverage distributions for the libraries with a certain number of vulnerabilities. For example, we plot a box plot for the libraries that have 0 vulnerabilities. Then we plot another box plot for the libraries with 1 vulnerability, then for 2 vulnerabilities, and so on. So as a result, we receive the plot as shown on the slide. If you just look at this plot, then the pattern is clear. As leverage increases, so does the number of vulnerability increases. Even though there are several exceptions on the very right on the plot, several libraries with the high number of vulnerabilities have relatively small leverage, even though the number of vulnerabilities is very high. We checked these libraries manually and discovered that these are exceptionally large libraries. They have a high number of vulnerabilities since they have very big code base. So they have more than 100,000 of lines of code. So if you want to heavily leverage on others' code, you have to accept a much higher security risk. But how much leverage on others' code is too much? In our sample, leverage that equals 4 seems to provide a visual separation between the libraries with high and low number of vulnerabilities. This corresponds to the observation we had in the beginning of my presentation. Dependency code is 4 times bigger than own code as industry average. Indeed, if we cover the top part of the plot, we'll see that mostly we have smaller number of vulnerabilities, except the very big libraries on the right of our plot that we already discussed. If we cover the bottom part instead, we will see the libraries with a high number of vulnerabilities. Hence, leverage equal 4 separates libraries with high and small number of vulnerabilities in our sample. Well, we already borrowed from finance. Let's also borrow something from medicine. Why not? In medicine, people are using the odds ratio analysis to understand the impact of a rare disease. In particular, odds ratio is the fraction of odds of disease if exposed and odds of disease if not exposed. In software, we can understand vulnerabilities to be such rare diseases. We can count a project as affected by a disease if there is at least 1 vulnerability affecting this project, and otherwise the project is healthy. On the other hand, we can use leverage threshold of 4 as a condition to count the project to be exposed and not exposed. After calculating all the numbers, we receive the following picture. So for small medium libraries with own code smaller than 100,000 lines of code in our sample, we have odds ratio equal to 1.61, which means that larger leverage leads to larger risk of being vulnerable. And for larger libraries, odds ratio equals to 0.43. So this means that larger own code leads to larger risk of being vulnerable. So for smaller libraries, the bigger risk comes from dependencies, while for big libraries, the bigger risk comes from own code. Okay, so we have observed that small and big libraries are different in terms of risk of having security vulnerabilities. Now, let's see how different they are in terms of leverage. So this slide shows the scatter plot with direct technical leverage on y-axis and own code size of a library on x-axis. So both axes have logarithmic scale. So we clearly see the relation between direct leverage and own code size. The bigger the library, the smaller the technical leverage. And the median technical leverage reduces from 15 for small medium libraries to 0.5 for big libraries. So the difference is more than 30 times. So rephrasing the idiom, little bodies have great souls, we observe that small libraries have great leverage. Or in other words, they by far ship others' code. Last but not least, we will see how the change direction metric allows us to understand the development trends in both small, medium, and big libraries. If we look at the top plot for the small, medium libraries, we can see the high peak around theta equals to 0 degrees. So this means that developers of many small, medium libraries in our sample preferred to adopt new dependencies. The next peak is around 180 degrees. This likely corresponds to the situation when developers removed some of their dependencies. For example, they could have done it due to the presence of security vulnerabilities introduced by these dependencies. Then we observe another peak around theta equals to 315 degrees. So developers of small medium libraries also substituted some functionality in their own code with the functionality coming from software dependencies. And a small fraction of libraries actually decrease their own code, which is represented by a small peak around theta equals to 90 degrees. Okay, now let's move to big libraries. We observe the highest peak when theta equals 90 degrees. So developers of big libraries actually tend to increase their own code. So remember the difference with the small libraries. We also observe that some of the big libraries adopted new dependencies along with the increase of own code of their projects. And a smaller fraction of big libraries focused on decreasing their own code. So these observations are very interesting because they allow us to see that developers of small and big libraries have different development strategies. So while the size of small libraries mostly affected by the changes in the amount of code coming from dependencies, developers of big libraries mostly focus on operations with own code of their libraries. To recap, the technical leverage is a simple yet effective metric that allows you to understand security risks of using dependencies in your software projects. This metric allows us to estimate and assess the trade-off of using software dependencies. For example, for the small medium libraries in our sample, the usage of dependencies pays off. The 4 times increase of the library code only requires time delay of a couple of days on average. But the same 4x increase in the total code size of a library means 60% increase of a chance to have a vulnerability in your library. If you are interested in the idea of technical leverage, we invite you to visit the techleverage.eu website. This website allows you to play a bit with technical leverage. For example, to learn some more details about this metric or to check technical leverage for some of the Java libraries in the live demo section. Also, you could check the section with related publications, related works, that contain the list of papers that introduce dependency metrics. You can check some of the empirical dependency studies or more lightweight magazine papers or blog posts about software dependencies. Thank you for your attention.